Take a look at this map that shows the global distribution of earthquakes. So my question to you is, how much useful geography could a typical GCSE pupil extract from such a map? Well, the answer is quite a lot, of course. There is a lot to be gained by looking at any map that shows something like this. But what I want to do in this short video is to take a look with you at what I see are some of the limitations of this as a way of representing the data, and some of the ways in which the GIS map can help to add value to exactly the same exercise, and why you might want to consider using it even as a teach from the front tool. So the question here is describe the global distribution of earthquakes. Of course, we'll all recognize what that pattern is, but I'm going to suggest there are a few limitations of using this map. The first one I would suggest is this. It's only going to show the locations. You have no idea of the magnitude or size of those earthquakes, and you can't do anything about that. The map cannot directly correlate with any other explanatory factors. As geography teachers, we of course will recognise the plate margins traced out by those earthquakes, but our students may not be able to make that connection right away, particularly if they've not yet internalised the map of plate margins. It might add to the cognitive load slightly of the task, and they can't add that directly onto the map. The data is, if you like, frozen in time, 1978 to 1987, that's really frozen in time. You can't update it with any other information than that. And if you take a look at the United States of America, it seems to suggest that the earthquake hazard isn't just confined to the west coast and California, but you can have earthquakes all the way through. But are these of all the same magnitude? You can't tell by looking at this data alone. And finally, the scale is fixed, so if you do happen to notice the pattern correlating to the plate margins, you will spot little anomalies like that in the middle of the Pacific Ocean. But because the scale is fixed, you can't zoom in and have a look. So in what ways might doing a similar exercise using GIS help to overcome these? Let's take a look. Okay, so this is very similar data represented on an ArcGIS map. You can see that I've put on a layer here of the global earthquake, slightly more up to date than the other map that I got, but nevertheless this is looking very, very similar. It's dealing with just the location data alone and no other layers on it. Now let's see how we can enrich this a little bit more, shall we? So the first thing that I said was that the regular map could only show the location and not change anything else about the magnitude. Let's see what the GIS map can do. So if we go in here and we change style, you can see that I'm showing location only here, but there's a whole bunch of different pieces of data represented in each one of those points of data there. So let's find magnitude. Let's add that on. Draw that up first, and all of a sudden you can see the magnitudes of the different size. Now, they're overlapping a little bit, so how can we tidy this up? Well, first of all, let's change the colour, shall we? Go to, say, that yellow colour, and let's put an outline around the edge so that we can see the different circles a little bit more clearly, like so. And let's move the distribution here to see if we can affect the sizing so that the larger ones stand out just a little bit more. How does that look? I can play around with that a little bit more, like so. And click OK and done. And all of a sudden we have got something an awful lot more data rich. Now, whenever I used this with my students, I said to them to describe the pattern, and very quickly they were able to spot the fact that this is a linear pattern here, and they could spot that it was related to the plate boundaries. In fact, I can even change the transparency of this a little bit to let them see the plate boundaries shining through a little bit more. So you've got multiple layers there, and you can see how they interact with each other. So what we've done there is had a look at more than just the location. We've also correlated it through to other factors such as the plate margins. But let's go in and have a closer look at North America, because what we said there was, what's the distribution like of earthquake hazards across North America? And you can see here when I asked my pupils to describe it, they talked about the linear pattern in the west coast, but they did talk about some of these clusters in here as well. Now, is there any way we can simplify this down a little bit more? Yeah, of course we can. Let's go in here to our global earthquakes, and this time I'm going to add a filter. You can filter all of the data here, so if I go on to magnitude again, and let's say that I want to have bigger magnitude earthquakes, bigger than magnitude 5, And I can apply that and it'll draw that down, and all of a sudden it simplifies the pattern out considerably. We can see that these big earthquakes are very much located here around the west coast, and all of those other little earthquakes were much smaller, that were sitting further inland and away from the plate margin. In fact, if we zoom out, we can see here that that corresponds, or that clarifies the pattern much more clearly, that the major earthquakes are found on or near the plate margins. But what of our anomalies? We discovered before with the static map that the scale was fixed, so my students noticed that there was something happening here. Let's go and have a closer look. We zoom in a little bit further and we can see this is Hawaii. But another thing that we can do, of course, with this map is to change the base map. So let's stick this on to imagery, which will give us a little bit more of an indication as to what the nature of this island would be. Now, it just so happens that my students will already have covered this and they'll know that this is a volcano, but it doesn't take much exploring here to see the volcanic nature of Big Island and Hawaii, with your caldera here and your lava flows coming down. This is clearly a very volcanic island, and if you've got magma chambers moving up in and around, you've got all sorts of tectonic activity taking place. It is no surprise that you're going to get some volcanoes occurring, or some earthquakes occurring here. Now, even if they don't know at GCSE about hotspots, even if they don't have to examine it, they can still take a look at the volcanic activity there, and they can have a look at that anomaly, and because you're in control of scale, you're able to work your way around that. But what about the dating of the data? This one is reasonably up to date, but what about some of the really recent earthquakes? Can you get unfrozen from time and find something a little bit more up to date? Well, yes, of course you can. If we type in recent earthquakes, hit enter, and we're going to add this on, just simply add this layer, and it's going to draw in all of the data and the more recent earthquakes. Now, I'm just going to go back and turn these global earthquakes on. This is time enabled, so I'm going to just drag that slider across so that we can see them all on there. And there are the earthquakes that are occurring. Now, you can see as you look here that a few of them are bigger earthquakes, and they've even got these labeled on where some of these bigger earthquakes are. But of course we can simplify the map down a little bit by taking a look at the filter. So let's go to the filter here, and our drop down menu here is magnitude, and we're going to say magnitude of greater than, again let's say a magnitude 5. We can apply the filter, and there you go. That immediately simplifies the pattern down, and you can go and explore some of these. You can see where the most recent earthquakes are that are occurring. Now, the thing that particularly caught my eye just before I was doing this exercise with the pupils, there was an earthquake in Alaska, and this information was here within moments of it actually happening, or within a reasonably short period of time of it actually happening. And what you're able to do is go and click on any one of those and you can find out a lot about it. Magnitude 7.4, that is big. There was a tsunami alert that had been given out with that. Now, you could explore the reasons why. If you've covered plate margins with them, you'll know that this is a destructive plate margin. And you're going to get a rebound up here whenever you get an earthquake like that. That's going to lift the seafloor and produce this tsunami risk. So you can explore all of that. You can see the trench. But you can also come in here and see, right, were there people living nearby? Were they under threat? You again come down here and see that this is what looks like a largely uninhabited island. So although this was a relatively big earthquake, there was going to be no people living nearby. But more than that, you can turn on something here called the shake intensity, because the magnitude of the earthquake is one way of measuring its impact. But what about the Mercalli modified scale, which gives you a sense of how it would be to experience that earthquake? Now, there is a key on here, but because this is a GIS map, you can click on that and again up it comes. This is, the intensity scale is a level 6, felt by all, many frightened, some heavy furniture moved, and a few instances of fallen plaster and damage is slight. So even though this is a very large earthquake, it's only up to about level 6. And again, if we come in here to this area where these islands are. I'll turn this back on again, and you can see that this is a relatively low population density area. In fact, it doesn't really look like there's anybody living there at all. I can change the transparency so that we can look in and out a little bit better with this. So it does look like, because of the location, this wasn't going to be causing an awful lot of problem for too many people. But I wonder if we come up here a little bit more, are we seeing places where more people are living? We can come in here and let's turn that layer off again. Again, it doesn't seem to be particularly densely populated. But there's something that's very interesting that just caught my eye when I looked. I wondered, did you notice it as well? If I turn that off and on, there seems to be a relationship here between the topography and the intensity of shaking. Let's zoom in right down here to this valley, because this definitely caught my eye. So the upland rocky areas seem to have less intensity of shaking than the lowland areas, which seem to be filled with soil. So you can talk about other factors, not just the size of the earthquake, not just the population density, but you can talk about the geology and the soil of the area. Where you've got rock, the intensity of shaking isn't as great. Where you've got soil, maybe it's amplified a little bit more. All because you can zoom on in and have a really close look at that particular earthquake. You're in charge of that scale. So I start off by saying, what powerful geography, what good geography can you do from the first map that I showed you? And yes, you can do some. But what I was hoping to show you here is just how much more geography can be unleashed, because you're in charge of how the data is presented, the way in which it's presented. You can bring in all sorts of different factors and variables as well. You're in charge of scale, and you're in charge of the time of the data. And because you have so much power over how the data is presented and the data you will access, I would suggest that you can access much more powerful geography for your students, even if you're using this just as a teach from the front tool.